Now, you'll notice that in this question, the transition is the same one referred to in the previous question on the energy change, and this saves us some time because we can use the same value of energy change from before. Previously, we calculated that the change in energy when the electron moved from n equals 5 to n equals 2 was 2.86 electron volts. Now, you could, of course, if you were given some other transition, figure out the energy there, but what we're asked to do is calculate the wavelength of the photon emitted. Now we know that the energy of a photon is equal to hc over lambda. And recall that basically what's happening here is we have all different energy levels around the nucleus, and we are moving from n equals 5 to n equals 2. So the electron is losing energy, and conservation of energy says that energy has to go somewhere. Sorry, I should have a minus here. It's decreased in energy. It's gone down 2.86 electron volts. Because the electron has lost energy, it will emit a photon with that amount of energy. So, rearranging our photon energy equation, we have the wavelength is equal to Planck's constant times the speed of light over E. And now, substituting in our values, we have Planck's constant times the speed of light over, we have our energy. Now, this is how much energy the electron lost, but the amount of energy the photon gained is just going to be the positive of that. So we've got 2.86. Now that's in electron volts. So in order to convert this to joules, we need to multiply by 1.602 times 10 to the minus 19. Now it's in joules. And so finally, if we are to put all of that into a calculator, we'll end up with a wavelength of 434 nanometers.